Japan. A country that faces hundreds of earthquakes every year. But how does this country survive earthquakes? The answer doesn't lie beneath the lifeless concrete blocks, but in the colossal machines that silently absorb every earthquake. This is the story of how the Japanese transformed uninhabitable lands into one of the safest, impossible places on the planet. Instead of bracing against the earth, they choose to move with it through nearly invisible damping technologies. Welcome to Japan, where hidden technology is redefining the lines between disaster and survival. Many people think Japan's earthquake-resistant system is just a bunch of 4.0 technologies, like the pendulum shock absorbers on 100-story buildings. But Biwako Sosui, built back in the Meiji era, is the real survival infrastructure. So why is Biwako Sosui a superior underground shield? As early as the 1880s, young engineer Tanabe Sakuro designed the canal system. Without relying on electric pumps or complex mechanical infrastructure, the water flows entirely by gravity. When major earthquakes disrupt the national power grid, modern pumping stations become paralyzed. But Biwako Sosui continues to supply water for domestic use, firefighting, and maintaining a continuous flow to Kyoto without consuming a single kWh of electricity. The tunnels through the mountains and open channels are reinforced with handcrafted fired bricks and flexibly stacked stones. This allows the structure to have slight elasticity when the ground vibrates, avoiding brittle fracture like that of modern rigid concrete pipes. In January 5, just 4 months after Kansai Airport officially opened, the mega earthquake of Kobe shook the entire region. While highways on the surface collapsed, and Kobe City was engulfed in ruins in Kansai, not a single pane of glass cracked, and passengers remained completely safe. The secret behind this extraordinary resilience lies in 3 core layers of technology located underground. Kix's biggest challenge wasn't just earthquakes, but uneven subsidence due to the island's location on soft clay soil up to 400 meters below the seabed. The 1.7-kilometer-long main terminal rests on over 900 massive steel columns. Each column base is equipped with highly sensitive leveling sensors and powerful hydraulic lifts. When a corner of the island subsides due to vibration or load, the computer system detects it immediately. Engineers simply lift the steel column and insert metal shims to keep the entire building perfectly flat. As a result, when an earthquake occurs, soil liquefaction, the leading cause of collapse of coastal structures, is almost completely eliminated. Look at Tokyo Skytree, the world's tallest freestanding television tower at 634 meters high. Have you ever wondered, how can such a towering steel giant stand so calmly through a series of super earthquakes without collapsing? The first key feature is the colossal reinforced concrete central column called Shinbashira in the center of Impossible Places. The marvel here is that Japanese engineers didn't invent it from scratch. They inherited the principles of traditional 5-story wooden pagodas. The Shinbashira column is 375 meters high and 8 meters in diameter, located right in the center of the tower. But the most valuable aspect is that this pillar is not fixed to the outer steel frame from 125 meters upwards. Below ground, the tower utilizes a system of petal-shaped steel piles, driven up to 50 meters deep, reaching the hard rock layer. Combined with a triangular base that gradually transforms into a circular shape as it rises, wind and vibration forces are evenly distributed 360 degrees. Many people think an earthquake-resistant structure must be extremely rigid. But with the Aqua Tunnel, the secret lies in the opposite thinking: absolute flexibility. It is constructed from tens of thousands of precast reinforced concrete slabs joined together in circular sections using shield-loading excavators. Between the concrete segments are a system of ultra-elastic, high-strength rubber joints. When seismic waves travel through the seabed mud, instead of resisting the pressure and fracturing, the entire tunnel will bend or curve. The joints both absorb the shock and maintain absolute water tightness under extremely high water pressure. by combining variable elastomer materials and energy-dissipating design. The Japanese have transformed what seemed like the most dangerous construction project, an underwater tunnel, into something truly dangerous. When a magnitude 9.0 earthquake swept through Japan, the Roppongi Hills Mori Tower, a 54-story giant in Tokyo, remained standing. At the heart of this technology is a system of 192 semi-active oil dampers, likened to intelligent hydraulic lungs. When seismic waves collide, ultra-sensitive sensors calculate the force of the vibrations in milliseconds. The computer system immediately adjusts the oil pressure inside the pistons to absorb the entire kinetic energy of the earthquake and convert it into heat energy. Whether it's short, powerful jolts from tremors or prolonged shock waves, Mori Tower doesn't resist the shaking, but actively responds. Combined with its ultra-durable steel frame structure and tuned mass dampers within impossible places, this tower not only protects the lives of thousands inside, but can even continue to operate normally immediately after an earthquake. This is not simply a matter of construction technique. It is the pinnacle of human ingenuity in the struggle for survival against nature. Imagine you're holding a cup of coffee at a height of nearly 230 meters in the heart of Tokyo. Suddenly, an earthquake warning sounds. The ground below ripples. But instead of terrifying, cracking sounds or violent shaking, this super tower reacts in a completely different way. To create an iconic structure spanning hundreds of thousands of square meters, Japanese engineers didn't choose to brutally confront nature. Instead, they concealed cutting-edge damping technologies within it. Similar to the expensive shock absorbers on supercars, a series of high-powered oil pistons are strategically installed throughout the tower's levels. As seismic waves propagate from the foundation upwards, these pistons immediately compress the fluid inside. As a result, the shaking is delayed and neutralized from the moment it begins. Many people think the white diagrid structure surrounding the building is just for decoration. In reality, it's a load-bearing steel frame in the form of a grid. When a super earthquake occurs, the shaking energy isn't concentrated in one corner or one main column. This digrid shell acts as an external skeleton, distributing torsional forces evenly across the building's 360-degree surface. Inside the cocoon is an extremely solid, reinforced concrete core within impossible places. But the most valuable feature lies in the hydraulic oil dampers connecting the outer steel frame and the inner core. When the ground shakes violently, these hydraulic pistons expand and contract flexibly. They function similarly to high-performance shock absorbers in cars, absorbing and neutralizing 30% to 40% of the shock energy from an earthquake. This building survived the earthquake thanks to its philosophy, a testament to the pinnacle of Japanese engineering ingenuity. Contrary to the common belief that a dam must be a solid, thick, monolithic concrete wall, Takase was constructed from millions of tons of boulders. Located in the center of the dam, this clay layer possesses natural plasticity. When an earthquake occurs, instead of cracking like concrete, this clay layer deforms slightly. Surrounding the clay core, keeping the fine particles from being carried away by the water flow. Millions of tons of stacked rocks form a natural shock absorber. Earthquakes transmitting mechanical waves through the rock mass will have their energy continuously dispersed between the gaps and points of contact. Seen from afar, Takase appears to be an integral part of the majestic surrounding nature, rather than a man-made structure. This is the pinnacle of Japanese engineering. Located right in the heart of the northern Japanese Alps, an area considered a hotspot for some of the most violent geological upheavals on the planet. Standing 186 meters tall, it's not only a masterpiece of hydroelectric power, but also an example of engineering immortalized by natural disasters. So what has helped this structure, weighing millions of tons of concrete, withstand earthquakes of magnitude on the Richter scale for over 60 years? Instead of resisting the immense thrust from the reservoir and earthquakes with pure concrete, Kurobe used an arch-shaped design. When an earthquake occurs, the entire force of the water and shock waves does not weigh down on the dam body but is naturally redirected. The two monolithic rock formations themselves act as two giants gripping the dam, absorbing up to 80% of the destructive energy. The biggest mistake in dam construction in earthquake-prone areas is making it too rigid in the middle of an impossible place. It is assembled from hundreds of individual concrete blocks with specialized expansion joints coated with a special type of asphalt. Born from the ashes of the devastating 2011 earthquake and tsunami, the Japanese government invested over $12 billion to erect this shield. With heights reaching 12 to 15 meters in many places, standing at the base of the wall completely isolates you from the ocean. The turbulent sea is reduced to the gentle murmur of waves, echoing from the other side of the solid concrete structure. However, the Great Wall of Japan is not simply a collection of stacked concrete blocks. The surface of the walls and the top section are not flat, but are cast with a curved shape based on exhaust gas and aerodynamic calculations. When a tsunami rises and strikes directly, this curvature will redirect the water flow back out to sea. It's well understood that no wall can completely stop a supersized tsunami. The secret to Ofunato's ability to withstand devastating tsunami-triggered earthquakes lies in its dynamic design philosophy. The wall is curved according to the principles of hydrodynamics in impossible places. When a tsunami hits, the energy doesn't directly tear the foundation, but is instead drawn outwards to neutralize the force with the subsequent wave. Underground, a system of reinforced piles extending tens of meters deep prevents the structure from collapsing due to soil liquefaction. The walls aren't completely sealed to serve the needs of the fishermen, but when seismic sensors detect strong vibrations from the ocean, the automatic wave gates slam shut within seconds without direct human intervention. Japan doesn't try to fight nature with absolute force. They use intelligence to navigate and disperse the power of the water currents. The Ofunato seawall is the most vivid example of that engineering philosophy. Stepping inside the dam through controlled corridors, dozens of meters deep underground, you feel the tremors from the outside world. biggest secret to the Yamba Dam's ability to withstand super violent earthquakes lies not only in its surface concrete structure, but also in its foundation, reinforcement technology, and next-generation gravity structure. Yamba is a 290-meter-long, 166-meter-high gravity concrete dam. Instead of traditional concrete, pouring in small blocks, the Japanese used RCD technology combined with seismic wave spectrum simulation calculations. The dam utilizes its own massive weight to anchor itself firmly to the bedrock. Japanese engineers drilled thousands of deep holes into the mountain and pumped special cement grout under extremely high pressure. This process solidified the entire surrounding mountain wall system, transforming the Yamba Dam and its slopes into a single monolith. Unlike many large-scale concrete dams that are prone to fracturing during geological faulting, Tokoyama is a compacted rock dam with a watertight core. The dam is constructed from millions of tons of rock, gravel, and clay that are extremely tightly compacted. When a strong tremor occurs, instead of rigidly resisting the earthquake force, the real secret lies in the hundreds of ultra-sensitive sensors embedded deep within the dam body and the underlying bedrock. These sensors measure pore water pressure, deformation, and vibration acceleration in real time. Thanks to the perfect combination of nature-inspired design and modern monitoring technology, Tokoyama Dam not only withstood numerous major earthquakes, but also protected millions of downstream households from devastating flash floods after the earthquakes. The Japanese don't try to defeat earthquakes. They learn to live with and absorb their force. Located on the border between Niigata and Fukushima Prefecture's Okutadami is Japan's tallest concrete gravity dam. Upon passing through the kilometer-long tunnel through the mountain to the base of the dam, Okutadami doesn't resist earthquake forces with elasticity, but uses its enormous mass to suppress shear forces. Millions of concrete blocks are pressed tightly into the solid granite bedrock, transforming the dam and surrounding mountain range into a single unified structure. Japanese engineers drilled thousands of holes deep into the ground, pumping high-pressure grout to fill every microscopic crack in the natural geology. When an earthquake occurs, seismic waves travel through the bedrock without causing landslides or dam failure. To avoid the risk of landslides from the mountaintop, damaging equipment during earthquakes. Standing on the observation deck and looking down at the vertical dam body, you'll see the astonishing smoothness of the concrete surfaces. Japan, a country that suffers hundreds of earthquakes and super typhoons every year. Yet why does it still stand strong? Many believe the answer lies in its high-rise buildings that dance with seismic activity. Consider the Kanda River underground balancing basin project. This isn't simply a stormwater drainage system, it's an astonishing geotechnical masterpiece. It's a massive cylindrical tunnel, 4.5 kilometers long and 12.5 meters in diameter, running beneath Ring Road number 7. The system's storage capacity is a staggering 540,000 cubic meters, equivalent to cramming 240 Olympic-sized swimming pools deep underground. The entire tunnel lining structure is cast from pre-stressed concrete blocks using shield tunneling technology. It is designed to both flexibly deform according to seismic waves from earthquakes and withstand pressure without a single crack appearing. If you have ever experienced a strong earthquake on the upper floors of a typical building, the violent shaking could knock anyone to the ground. But standing at Tokyo during a major aftershock, the experience is completely different. The building doesn't break or shake wildly, but bounces rhythmically like a ship navigating rough waves. This miracle isn't accidental, but the result of 3 layers of core technology that the Japanese have installed inside this superstructure. Tokyo is not just for self-preservation. The building is designed to be Tokyo's highest-level disaster response command center. Hundreds of seismic accelerometers scattered throughout the building will instantly activate the emergency mode within milliseconds. The Japanese don't try to defeat earthquakes with brute force. Instead, they use intelligence to absorb, redirect, and live with them. The Tokyo Metropolitan Government Building is the most vivid example of this Vietnamese architectural philosophy. When mentioning Japan's earthquake-resistant engineering masterpieces, people often think of Tokyo's Skytree. But Abeno Harukas in Osaka 300-meter-tall tower is the pinnacle of the combination of ancient wisdom and futuristic technology. Japanese engineers incorporated the Shinbashira central pillar principle into the core of Abeno Harukas. During an earthquake, the concrete core and outer steel frame do not move in the same direction, but instead rotate out of phase with each other. This helps to dissipate much of the vibrational energy released. Inside the Abeno Harukas structure are a series of high-pressure oil damping systems and megatruss frames. When an earthquake occurs, these dampers act like giant piston cylinders, absorbing 40% to 50% of the shock force. The tower doesn't brace itself to collapse, but actively glides with the rhythm of the seismic waves. Imagine yourself standing nearly 300 meters atop the steel bridge towers on the morning of January 17, 1995. The Great Kobe earthquake struck right below its epicenter, just a few kilometers from the construction site. The two colossal towers of Akashi Kaikyo, even though the bridge girders were not yet fully connected, remained firmly standing. The slip of the geological plate that day pulled the two towers apart by exactly 1 meter. Instead of collapsing, the flexible steel structure and clever expandable design allowed engineers to simply adjust the cable length and continue construction. This is the most valuable testament to the strength of Japanese engineering. Inside each 297-meter-tall steel tower is an incredibly sophisticated motion control system. A total of 20 massive pendulum dampers are suspended inside the tower. This is the Kanda River underground reservoir, a masterpiece of Japanese civil engineering. A massive reinforced concrete tunnel, 12.5 meters in diameter and stretching over 4.5 kilometers, runs underground beneath the city. When storms pass, floodwaters from the Wada and Zenpukuji rivers no longer inundate residential areas. Instead, all excess water flows into this underground reservoir with a capacity of up to 540,000 cubic meters. Many people think underground structures are very susceptible to collapse during earthquakes, but the reality is quite the opposite. When an earthquake occurs, the cylindrical underground structures distribute stress evenly, withstanding the force far better than above-ground buildings. This structure serves both as a pressure relief valve to rescue the city from flooding after natural disasters. It exemplifies the Japanese concept of proactive defense, not fighting against nature, but creating space to regulate its power. Consider the Miyagawa Dam, a quintessential Japanese concrete fortress for holding back water. The secret to its ability to withstand the Earth's fury lies not in creating a rigid concrete structure to resist the Earth's. Instead of being cast as a single rigid block, which is easily torn apart by terrain deformation, the Miyagawa Dam is assembled from many independent concrete blocks connected by specialized seismic expansion joints. The Miyagawa Dam's foundations are not simply placed on the surface. This transforms the entire dam and the underlying foundation into a single, unified structure. When the earth shakes, the dam will vibrate at the same frequency as the bedrock, instead of being out of phase, avoiding collapse due to resonance. While traditional buildings rely on rigidity, Toranomon Hills utilizes the principle of softness, softened by rigidity. Scattered throughout the building's steel frame are ultra-heavy oil-filled pistons. When an earthquake occurs, the earth shakes violently, and these pistons move back and forth, compressing the fluid inside and creating enormous resistance. These bars are arranged diagonally in the steel frames. A person standing inside during a strong earthquake will not feel dangerous jolts. But only see the building swaying, very slowly and gently, like a yacht gliding through large waves. To prevent a megacity weighing hundreds of thousands of tons from collapsing the tunnel, the foundation system, the structure of the underground tunnel and the structure of the tower are completely separate. Imagine the enormous Nissan Stadium with a capacity of over 72,000 people not resting on the ground. But instead elevated by hundreds of super-heavy, reinforced concrete pillars. Record-breaking capacity up to 3.9 million cubic meters of water, equivalent to nearly 1/600 standard Olympic swimming pools. Around Yokohama, torrential rain poured down, nearly overflowing many rivers. But here, the automatic sluice gates opened. The Tsurumi River surged into the reservoir beneath the stadium. During that storm, Lake Tsurumi swallowed a total of 1.57 million cubic meters of water, setting a record for the largest flood discharge in the dam's history. Japan doesn't try to fight nature with rough concrete walls that block the view. They choose to give space to water. The Tsurumi River multi-purpose regulating basin is a vivid example of this cutting-edge planning thinking. Many people think Japan's earthquake-resistant system is just a bunch of 4.0 technologies, like the pendulum shock absorbers on 100-story buildings. But Biwako Sosui, built back in the Meiji era, is the real survival infrastructure. So why is Biwako Sosui a superior underground shield? As early as the 1880s, young engineer Tanabe Sakuro designed the canal system. Without relying on electric pumps or complex mechanical infrastructure, the water flows entirely by gravity. When major earthquakes disrupt the national power grid, modern pumping stations become paralyzed. But Biwako Sosui continues to supply water for domestic use, firefighting, and maintaining a continuous flow to Kyoto without consuming a single kWh of electricity. The tunnels through the mountains and open channels are reinforced with handcrafted fired bricks and flexibly stacked stones. This allows the structure to have slight elasticity when the ground vibrates, avoiding brittle fracture like that of modern rigid concrete pipes. In January 5, just 4 months after Kansai Airport officially opened, the mega earthquake of Kobe shook the entire region. While highways on the surface collapsed, and Kobe City was engulfed in ruins in Kansai, not a single pane of glass cracked, and passengers remained completely safe. The secret behind this extraordinary resilience lies in 3 core layers of technology located underground. Kix's biggest challenge wasn't just earthquakes, but uneven subsidence due to the island's location on soft clay soil up to 400 meters below the seabed. The 1.7-kilometer-long main terminal rests on over 900 massive steel columns. Each column base is equipped with highly sensitive leveling sensors and powerful hydraulic lifts. When a corner of the island subsides due to vibration or load, the computer system detects it immediately. Engineers simply lift the steel column and insert metal shims to keep the entire building perfectly flat. As a result, when an earthquake occurs, soil liquefaction, the leading cause of collapse of coastal structures, is almost completely eliminated. Look at Tokyo Skytree, the world's tallest freestanding television tower at 634 meters high. Have you ever wondered, how can such a towering steel giant stand so calmly through a series of super earthquakes without collapsing? The first key feature is the colossal reinforced concrete central column called Shinbashira in the center of Impossible Places. The marvel here is that Japanese engineers didn't invent it from scratch. They inherited the principles of traditional 5-story wooden pagodas. The Shinbashira column is 375 meters high and 8 meters in diameter, located right in the center of the tower. But the most valuable aspect is that this pillar is not fixed to the outer steel frame from 125 meters upwards. Below ground, the tower utilizes a system of petal-shaped steel piles driven up to 50 meters deep, reaching the hard rock layer. Combined with a triangular base that gradually transforms into a circular shape as it rises, wind and vibration forces are evenly distributed 360 degrees. Many people think an earthquake-resistant structure must be extremely rigid. But with the Aqua Tunnel, the secret lies in the opposite thinking: absolute flexibility. It is constructed from tens of thousands of precast reinforced concrete slabs joined together in circular sections using shield-loading excavators. Between the concrete segments are a system of ultra-elastic, high-strength rubber joints. When seismic waves travel through the seabed mud, instead of resisting the pressure and fracturing the entire tunnel, will bend or curve. The joints both absorb the shock and maintain absolute water tightness under extremely high water pressure. By combining variable elastomer materials and energy-dissipating design, the Japanese have transformed what seemed like the most dangerous construction project, an underwater tunnel, into something truly dangerous. When a magnitude 9.0 earthquake swept through Japan, the Roppongi Hills Mori Tower, a 54-story giant in Tokyo, remained standing. At the heart of this technology is a system of 192 semi-active oil dampers, likened to intelligent hydraulic lungs. When seismic waves collide, ultra-sensitive sensors calculate the force of the vibrations in milliseconds. The computer system immediately adjusts the oil pressure inside the pistons to absorb the entire kinetic energy of the earthquake and convert it into heat energy. Whether it's short, powerful jolts from tremors or prolonged shock waves, Mori Tower doesn't resist the shaking, but actively responds. Combined with its ultra-durable steel frame structure and tuned mass dampers within impossible places, this tower not only protects the lives of thousands inside, but can even continue to operate normally immediately after an earthquake. This is not simply a matter of construction technique. It is the pinnacle of human ingenuity in the struggle for survival against nature. Imagine you're holding a cup of coffee at a height of nearly 230 meters in the heart of Tokyo. Suddenly, an earthquake warning sounds. The ground below ripples. But instead of terrifying, cracking sounds or violent shaking, this super tower reacts in a completely different way. To create an iconic structure spanning hundreds of thousands of square meters, Japanese engineers didn't choose to brutally confront nature. Instead, they concealed cutting-edge damping technologies within it. Similar to the expensive shock absorbers on supercars, a series of high-powered oil pistons are strategically installed throughout the tower's levels. As seismic waves propagate from the foundation upwards, these pistons immediately compress the fluid inside. As a result, the shaking is delayed and neutralized from the moment it begins.